Hello everybody, and welcome to another installment episode. I don't know what to call these. Welcome to another Back to Basics video. This week we're going to be talking about capacitors. Let's get that back in shot, shall we? There we go. This week we'll be talking about capacitors. Now, there are 4 types of capacitors, generically. We have ceramic capacitors, which will be these little tiny, typically sort of brownish blobs of ceramic. They tend to be able to handle higher voltages, but have lower capacitance. We have metal film capacitors, which look like these. These tend to be higher voltage with a lower, medium to low capacitance. You'll have seen a lot of these in my live stream where I built an ionizer. And then you'll also have electrolytic capacitors, which are these sort of can-type capacitors. They tend to have higher capacitance, but lower voltage ratings. And then there are also tantalum capacitors, which are sort of a hybrid of ceramic and electrolytic. They are polarized like electrolytic capacitors, but they can handle they hold a great deal more capacitance in a much smaller package. They don't tend to have a very high voltage rating. And there are also, oh no, I already mentioned metal film capacitors. So anyway, what is a capacitor? Well, it's a device that holds voltage. It has a capacity to hold voltage. Now, the basic premise of a capacitor is you have a conductive plate and then some sort of insulating material and then another conductive plate. And you apply a voltage across these plates, and although the voltage can't actually pass between these lines, what you get is a bunch of electrons that really want to flow over to this side of the capacitor, but they can't. So they just sort of collect there. And then that builds up to a certain point, and then it can't hold any more capacitance. And then if there's a drop in voltage or a fluctuation in the power supply or any number of different reasons, those electrons will then start to flow back out and provide a current flow back into the circuit. So how are capacitors built? That's the main thing that we're going to be talking about in today's video. Where's my eraser? There it is. So let's start by talking about ceramic capacitors. Now, ceramic capacitors are, let's see, what colors do I want to use here? You'll have a lead coming up to a plate, and it's going to be attached to a bunch of plates like so. And then you'll have another lead coming up on the other side, and it will be attached to a bunch of plates like so. You'll notice that they don't actually touch. And then in between these, I bet that's not even going to show, so I won't use yellow for that. Let's use red. So in between these, in here, is going to be a ceramic material that is non-conductive and has a very low permissivity, which means it doesn't allow a magnetic field to build up in it either. And the electrons will build up on the negative side of the plates, and then they'll flow back out when the voltage is removed from it. Now, the next type of capacitor that we can talk about is well, actually I'll leave metal film capacitors for the last, because we're actually going to be doing a practical demonstration. So let's talk about electrolytic capacitors. How do I want to draw this one? We'll use red and blue. So with electrolytic capacitors, they're a little bit more complicated due to the fact that they are polarized. Now, they're typically wound in a tight spiral, but I'll just simplify the construction here just by drawing straight lines. So we're going to have the positive anode coming in. Yeah, the anode. Oh, bugger, I can never remember. Anyway, we'll have the positive side coming in there, and it's going to have, say aluminum is the most common one, and it's going to have a thin layer of aluminum oxide on one side of it. And then between that and the next layer, we're going to have a piece of paper that's soaked with an electrolyte solution. And then we'll have the negative lead, which is going to be non-etched aluminum. It's just going to be regular aluminum foil. And then, I need one more color for this. We'll use purple. And then you have a paper spacer. And they take that and they wind it up really, really tight. Because of the fact that the insulating layer here is this layer of oxide, that's actually the dielectric layer there, and the electrolyte here is meant to increase the amount of electrons that can build up. It is very important that these are polarized, because if you connect them backwards, you'll just get flashover that's going to destroy this oxidizing layer, and then it'll ignite the electrolyte, and there'll be smoke and potentially flames, and the electrolytic capacitor will explode. I actually had a instructor that was fond of catching the class's attention by blowing up electrolytic capacitors. He would also leave high capacity capacitors, like big 1 farad ceramic capacitors, just laying on the workbench, and we very quickly learned to ground any capacitor that was just laying out, because he'd charge them and then you'd grab it and it would give you a bit of a zets. And it was more of a practical lab safety demonstration, I think, that he was trying to get at. But anyway, so that's why electrolytic capacitors are polarized, because there's only one side of the capacitor that's actually built to accept the buildup of electrons. Now, I hope I can draw this well, because tantalum capacitors are a little bit more complicated. I'll only draw 1/2 of it, but you'll have a tantalum wire here, and around that wire will be compacted tantalum powder. And you'll get these little balls of tantalum, and they'll sort of overlap, and maybe you'll get a big one, and then a really big one, and then a little one, and a little one, and so on and so forth. You get all these pieces of tantalum that are all compressed against each other. They're sintered. It's the way magnets are made as well. So you get all these particles of tantalum, and there are open spaces inside them, and this is actually important because Then on the powder, they oxidize it, so you have a layer of tantalum pentoxide all on the outside of these little pellets of tantalum. Like so. And there may be some in here, and then a little bit over there, and some over here, and in there. All in the gaps. And then, on top of that, what color should I use for this? I'll use black. On top of that, there's going to be a slurry of manganese dioxide. Now this is the electrolyte layer. This is the layer that increases the amount of electrons that are permitted to build up inside, and you'll have the electrolyte building up all throughout inside. And then last layer of material is going to be a layer of graphite. And that's mainly just to finish the conductivity. And also imagine that these layers are going all throughout these little tantalum particles. I did not draw this particularly well. And then last but not least, you'll have the cathode, which is silver, and it's going to come over here and attach to that, and then there'll be other particles, so on and throughout there. That's not a terribly good drawing, but that's how a tantalum capacitor works. And due to all those pores inside the sintered chunk of tantalum, and then the layer of tantalum pentoxide, and then the manganese dioxide slurry, you can cram a great deal of capacitance into these tantalum capacitors. The only issue being, of course, that they don't have a great voltage rating. All right, so our last our last type of capacitor that we'll talk about is the metal film capacitors, and they are super simple and very easy to make, and we're actually going to make a couple here as part of the video. So a metal film capacitor, you're going to have a conductor, typically aluminum, but there can be other things, and then a layer of insulator, generally paper, and then another conductor, and then another layer of paper. And then they roll that up really tight, or they fold it back and forth, or any number of different methods of cramming it all into a thing. Like these will be a bunch of layers folded back and forth, or like when I drew the picture of the ceramic capacitor, there will be layers that are just sort of combed into each other, but these are not polarized. They don't have to be, because there's no electrolyte layer, there's no oxide layer, there's nothing like that. There's just metal, and then a dielectric layer of paper, and then more metal. Or sometimes there's the PVC film or something like that. Anyway, so let's go ahead and have a little bit of fun, and let's make a metal film capacitor. So, pardon me a moment while I just put my whiteboard off to one side. Alright, I'll get my watermark up there. And where is my thingy? There it is. Alright, so let's make a small capacitor. Now, I'm just going to pull out a section of, this is just regular baking parchment. Let's just cut off a piece like so. Now, I've seen other demonstrations of this done with that metal ducting tape, or sometimes it's a, oops, this is not the current one. The aluminum tape with the sticky backing. It's used for ductwork or insulation, or various other things. I sometimes use it as grounding tape in various projects, but I don't have any of that, so we're just going to make do very carefully with some aluminum foil. Sorry for the crackling noises, headphone users. So, let's just rip off the section of aluminum foil there. And going to be a brief blip here. Hang on just a second. And we're back. We were almost at maximum file size on that video, so I figured I'd quickly reset the timer. So, let's see if we can carefully cut some foil here. Again, many apologies to headphone users. I'm sure that's not quite pleasant. Alright, that's good enough. This isn't going to be perfect by any means, but it will demonstrate the properties for us. Alright. Now I just need, where did the tape go? There it is. Here's where headphone users are really going to hate me. There we go. Oops. Ah. Alright, well, I guess we're going to have to make the best of it with that. That's really a very terrible job there. Alright, and then we'll iron that down a little bit more with some more tape. And then I'm going to make one of our electrodes here by just stripping a piece of wire, laying it against the aluminum foil there, and then taping it down. Now this is going to be a very tiny capacitor. This is not going to have a great deal of capacitance at all. But this is just to basically prove the concept. Alright, so we're going to flip this over now and slice another piece of foil here. I'll just do it quick off camera here, or out of shot rather. And then just trim off a little bit of this here. There we go. And we'll tape that down. Like so. You'll notice that I'm being careful to make sure that the metal doesn't actually touch the other side. This is very important. You don't want it grounding against the other side, otherwise all of the electrons that you're storing up flow right over and go away. So it's important to make sure that there's good separation. Mark? Oh, no, never mind. I was yelling at my cat there for eating the wrong food, but it wasn't the wrong cat, so he's fine. Anyway, so let's just finish taping this down, and we'll see if we actually get a salient reading off of it. So, let's make sure that's nice and tight. I'm going to go ahead and quickly trim off the excess tape here. There we go. And trim that off. Alright, so that is a very, very basic metal film capacitor. We've got two pieces of foil with a dielectric layer between them, the dielectric layer being the tape, or the dielectric layer being the silicone-infused baking parchment. And let's see if we can get a reading off of it. Alright, so we're getting about 250 picofarads. Now, I was waiting for this part in the video to discuss how capacitors work. Surface area is a very important thing with capacitors. The larger the surface area and the thinner the dielectric, the better. Of course, the thinner the dielectric is, the lower your penetration voltage is, so you can make a really, really thin dielectric and have very high capacitance, but only a very low voltage rating for it. So the more surface area we have, the greater the amount of foil that we have on each side, the more capacitance we're going to have. Now I'm going to go ahead and prove that by cutting this in half. So we had about 250 picofarads before. Let's see. Oops, where are you? There we go. Let's see what we have now after cutting it in half-ish. Look at that, 179 pico. Well, 180. And if I squeeze this tight, it's going to go up a lot. And then it'll go back down if I just let it be. So you can see when I have the surface area of the dielectric and the conductors, it have the amount of capacitance. Now, just for fun, and I did this off camera, I supersized this project. So, oops. Going to punch my camera. That's a very important first step there. I'm going to zoom way out here. I'm going to bring in my supersized capacitor. Now what I did here was I took a pool noodle and around it I rolled about 10 feet of aluminum foil and the baking parchment. So, and then I've got my electrodes here on either end. So let's go ahead and find out. I already know, but I'm going to show you guys what the capacity of this thing is, and also give you an idea of just how thin the film actually is in these capacitors when they're built, by industrial standards. So this capacitor measures at 296 nanofarads. That's a pretty big capacitance considering it's homemade. But this little guy here is, what are these again? 0.22 micro, so 220 microfarads, which is, 222 picofarads, 0.22 micro. And this is 0.22 micro, 296 nano. So, there is an equivalent number of layers of metal foil and polypropylene film in this capacitor as there is sitting here on my desk, just to give you an idea of the miniaturization that is possible with capacitors. Now, I'm probably going to do a bonus video somewhere here in the next couple of days where I'm actually going to test the dielectric strength of this capacitor. And by test the dielectric strength of this capacitor, I mean I'm going to pump voltage in it until it starts to smoke, which means that I've broken down the dielectric barrier between the layers of foil. I won't do that this time around, but I just wanted to show you that you can, in fact, build a capacitor, and there's a proof of concept there with the foil cutting it in half, showing you how the area of the conductor and dielectric is proportional to the amount of capacitance. So thank you so much for joining me. This is probably one of the most involved videos I've done so far. If you'd like to see more of these, I've got big plans in the future. Go ahead and click here to subscribe. There's also a bell icon down near the video description. You can click that to get notifications of new videos. Right over here I'll have a video that YouTube thinks you'll find interesting based on your watching habits. Over here will be the Back to Basics playlist, and right here will be a Patreon link that you can use to help fund more videos like this one. So thank you so much for watching, and we'll see you next week. Bye-bye.